Oh, thanks, Professor Deng, for the nice introduction. So today I'm going to talk about generalization error and the implicit bias of grading method for deep learning. So this is a joint work with Xuanyuan, Mingda, and Kaifeng. So everybody know that deep learning works very well, and it has its underlying multi-trillion-dollar business. But the deep learning theory is the development of deep learning theory is way behind of the deep learning practice. But in the recent years, there has been some very exciting results. So in the NIPS 2017 conference, the Ali Rahami, the winner of the Test of Time Award, says that the machine learning has become alchemy. And his statement has raised a lot of attention, and the Turing Award winner Yann LeCun was not happy with his statement, and there was a big debate online. But no matter which side is right or wrong, we all agree that we still don't have a very satisfying theory about deep learning. And there are many mysteries about deep learning. So first of all, it's highly over-parameterized, meaning that the number of parameters is much more than the number of training data, and therefore the traditional learning theory does not work directly. And also it's highly non-convex and has many local or global minima, and make the optimization very non-trivial. And also people have believed that the training algorithm, especially the gradient-based algorithm, for example, the stochastic gradient descent, have played an important role. And this has led to the some algorithm-dependent generalization, or maybe there are some implicit bias about those algorithms. For example, those algorithms may find some local or global minimal with interesting property. And also there are like inductive bias. For example, why the convolution works so well for the image data, and this is still mysterious. And also why the deep learning can learn the very nice representation in a hierarchical way. And the talk after mine was given by Jason Lee from Princeton, and he will talk about learning representations in deep learning. And there are also many useful tricks, such as the dropout, batch norm, layer norm, or different initialization. All are very important for the training of the deep learning. And all this combines make deep learning very mysterious. And in this talk, I will talk some aspect of deep learning, especially the algorithm-dependent generalization and the implicit bias. So let me talk about generalization error. So this is a very central concept in machine learning. Basically, it matters that the hypothesis obtained from the training data can generalize to a new data point. And the notion is very well studied in a convex setting, and we have a very, very nice and classical theory about uniform convergence, and there's huge literature on this. And the formula mathematically is defined as follows. The generalization error is defined as a difference of two quantities. And the first quantity is the population loss, which is something that we truly want to minimize. We want to minimize basically this is a testing error. And this is a training loss minus the training loss. The training loss is the loss we get from the training data. And typically in the deep learning regime, typically we can make the training loss very, very small, meaning that we somehow overfit the training data. And if we can prove the generalization error is small, then we can see that the population loss is small, okay? So hopefully the generalization error is small for certain training data and certain training algorithms. And this is a classical learning theory, and it's very famous VC dimension on the Render-Maher complexity. And they claim that the generalization error roughly scales as follows. It's a square root, and in the denominator is a complexity, the numerator is a complexity, and typically, and the n is the number of training data. typically the complexity is larger than the number of parameters, and which is, as I mentioned, in the deep learning regime, the number of parameters is much larger than the number of training data. So therefore, this generalization error, according to the classical learning theory, is larger than 1. And for example, if we look at 0-1 loss, if the generalization error is larger than 1, it's meaningless. Therefore, the classical learning theory cannot explain what's happening in the deep learning regime. And also, the complexity typically only depends on the hypothesis class. For example, in deep learning, the hypothesis class is all the neural network with a certain number of parameters. And actually, what we really need is a data-dependent bound. The generalization error should depend on the data, and this will. So I'm going to explain this by the random label, very famous random label experiment, so which I'm going to show shortly. So this is John et al.'s work, the random label experiment, and which was published in iClear 2017. And they did very interesting experiment. So basically, they have two different kinds of data. So one is a normal image data, so image classification task. And the other data set is a random label data set, meaning that for each picture, they assign a random label. So they fit both data set to a reasonable neural network. And they can see that, so the neural network can fit both data set. For example, this blue curve, and this is a red curve. The blue curve corresponding to the normal data, the true labels, and the red curve corresponding to the random labels. We can see that for the normal data, so it converge very fast, but for the random label, it still converge, meaning that the neural network can still fit the data perfectly during the training, although it's a little bit slower, roughly about 3 times slower. Okay, but let's look at the generalization error. So they are very different. So this picture shows that the training error for both data sets would be almost close to 0. But for the generalization error, as we can see, so the x-axis is a proportion of the label corruption, meaning what's a proportion of the data we assign random labels. So we only need to look at here. So this is a perfect label, so the true label, and this 1-0 means we random perturb all the labels. So here we can see that, for example, let's look at the inception network. And so for true labels, it's almost, the testing error is almost 0. But for the purely random labels, so the testing error is 0.9. So the experiment is done on CFR10, which has 10 classes. So random guess would achieve testing error 0.9. And so if we gradually change the proportion, then this is the curve we can see. And they did experiment on several neural networks, and all have the same trend. But this means we have the same neural network. So basically, it's the same neural network. According to the classical theory, it should give us the same generalization error. But now, for different data with different labels, we have very different generalization error. Therefore, we need a data-dependent bound. And there are some previous work on this. And for example, Hart et al. And Mo et al. Argue that, so if you can train the data faster, you can generalize better. So their argument is essentially from this observation that for normal data, so we can train somewhat easier. But the key question is that, I mean, their argument is reasonable, but as we can see that for the training, the random label data is only a little bit harder or slower than the true label data. So, but their generalization is drastically different. So perhaps we need some better quantity to quantify this difference. And of course, there are many other perspectives. And there are many related work during the past few years. And the researchers have looked at the generalization from many different perspectives. For example, they look at the shape of the minimal, or they study this from the margin perspective, or they use, for example, random marker complexity or packet Bayesian framework. Those framework are developed before the deep learning theory, but they use those framework more carefully. And of course, there are, in the past 2 years, there are some new breakthrough in deep learning theory. For example, the neural tangent kernel or mean field analysis, and the very new double descent phenomena, which I don't have time to talk in detail today. So my first work is concentrated about the so-called algorithmic stability, which is also a very famous framework for proving generalization errors. So now let me talk about the main algorithm that we are interested in. So this is the gradient descent dynamic. So basically, we update the parameter, and each time in the negative gradient direction, and we can make this stochastic by just compute the gradient from a mini batch, or if we compute it from full data, it's a full gradient. But it turns out that in order to use the algorithm stability framework, so the stochastic gradient descent or gradient descent is very hard to analysis. You can still analyze it, but it gives you very bad bound. So instead, we analyze a close variant called stochastic gradient Langevin dynamic. It's very similar to the gradient descent, but only we add a small noise term. So this term is isotropic Gaussian noise. So the variance is a sigma t over square root 2, and that everything else would be the same. So basically, each time we go to the negative gradient direction and add a small Gaussian noise. And actually, sometimes if you add some extra noise, this is very helpful also in practice, but sometimes it's not so useful. And this is analyzed empirically by Zhu et al. Okay, but if we consider the very small step size, the learning rate goes to 0. Actually, we have this so-called Langevin dynamic. So this is stochastic differential equation, and this has been studied extensively in the physics literature. And people know that actually we can derive that if you continue this dynamic for a long time, it will converge under certain assumption. It will converge to a stationary distribution. Will roughly look like this. It's proportion to the e to the power of minus beta fx. Beta is this proportion is actually a temperature parameter. And for example, let's look at this this figure, and we have this function. This is let's see, this is a fx. This is a function, and the stationary distribution would be distributed like this. And for around the minimal, we have most of the probability mass. But this is only holds for the stationary distribution. And actually, it's known that for non-convex setting, it may take a long time to reach the stationary distribution. Therefore, we cannot assume a stationary distribution, but only give you a finite time analysis. Okay, so now let me talk about our result. So we look at this dynamic, which is a stochastic Langevin dynamic. We can have either the full gradient or a mini batch gradient. So in both cases, our theorem applies. And so our theorem is the following. So suppose the loss function is C-bounded, meaning that the loss function is positive and less than c, and the batch size is smaller than t over 2, and we have this gamma t is the learning rate, and we get this following generalization bound. It's a little bit long formula. Let me just parse it for you. And it's n is a number of parameters, and n is a number of training data. So if we have more training data, the generalization will become smaller and smaller. And the c is the c bounded, which is you can think as a constant. So the most important part inside this square root is a summation. This is a summation from the 1 to t. T is the number of iterations. And in each iteration, we sum up, basically, this is the norm of the gradient square. So it's a square gradient. You can either measure it empirically or measure it in the population sense. So both way works. Okay, and this is the gamma t is a learning rate, and this is a noise level. So you can think both as a small constant, and you can ignore this. And roughly, it's basically this big sum is a sum of the gradient norm square along the training trajectory. Okay, so it's fairly easy to remember. So first of all, our bound is independent of number of parameters, and also in practice, the number of iterations is much smaller than n square. So if you think this as a constant, so basically this term is much smaller than n, so it will give us meaningful bound. And also you can see here, so if you have a larger noise adding to this iterations, actually this is helpful for generalization. So larger noise helpful for generalization, but it hurts optimization. So we have done experiment. If you add the very big noise, it will converge very slowly. So it's basically a trade-off. So you need to trade off the size of the noise. And this theorem is proved by actually a new Bayes stability framework. So it combines the Peck-Bayesian framework and the algorithmic stability framework. I don't have much time to go into the technical details. But just to compare our result with the previous one. So previously in Hart et al., for the convex bound, they proved the following convex bound, but we are mostly interested in the non-convex case. And in the non-convex case, they gave the following bound. So, but their bound is under a very strong assumption that the step size gamma t is less than c over t. That means that the step size gets smaller and smaller, and it sort of converge very fast. But this is not what we do in the deep learning practice. Usually we use a constant step size for a long time, and then we decrease the step size. So therefore their theory is not apply to our current modern deep learning practice. And the most closely related work is by Mo et al. And their bound is looks like following. It's very similar to our bound, except that they have this L, which is the worst case Lipschitz constant. And we know that for neural network, this Lipschitz constant could be very large. And we replace their Lipschitz constant with this actual gradient, the norm of the gradient, norm square of the gradient, and it's strictly less than L square. I just want to mention that in our experiment, initially this value, this gradient square is very large, and as we training till the end, it gets very smaller and smaller. And there are some other benefit about our bound. In particular, actually, our bound is a so-called a pathwise bound. Therefore, actually, you can have some other operations on our trajectory. For example, if we take the average of all the steps as our final solution, or take the average of surface of a certain length as our final solution, our bond still holds, but this bond doesn't hold for Mo et al. Their analysis doesn't support such operations. And also our bond has a much simpler proof. And another very related work is by Pense et al. And they gave a pathwise analysis, and but their bond only scale with square root n, not 1 over n. But their bond holds for high probability, but our bond only holds for in expectation. And if you look at high probability bond, there must be a square root n term there. Okay, so we can also extend it to, for example, if you add some momentum or add some acceleration to the dynamic, or have some other variant, for example, the entropy SGD, some other optimization algorithms, our method also applies, and it can also be applied to some other continuous noise. So let me apply our bond in some experiment. So first we did a very toy experiment. So we make CFAR10 into a binary classification problem. Basically, if the label is less than 5, we make y equal to -1, otherwise y equal to 1. So it's a binary classification. And we train the neural network, and we compute this value. And so let's look at this figure. So this figure is about the generalization error or testing error, because the training error is almost identical to 0. So you can see for the normal data, so this is a blue lines. It's very, very small. And if you have a random label, so this testing error is close to 0.5, oscillating around 0.5 because it's a random guess. And if you plot this big summation here, and we can see in the bottom of the figure, and this for normal data, we have this curve, and for the random label data, it has this curve. And you can see that the trend of the generalization error and our bound are very, very similar, and there's a huge gap. And here we also have a very huge gap. And we have done a similar experiment on more data and more architectures. For example, for MLP on the CFAR10, we can see that the training accuracy converged to 100% very quickly, and the generalization error is look like this. And here, even for normal data, its generalization error is not very good because it's MLP. It's not very good for image data. And let's look at the last picture. This is a summation of the empirical norm square, and you can see the trend is very similar. And we also done the experiment on AlexNet, and you can see the trend is also very similar. So for generalization error and our bound, their trend is very similar. Of course, the absolute value are not the same. So here, this is between 0 and 1. Here we have around something less than 20. It's still small, pretty small comparing to other theoretical work, but it's still, in most of the regime, it's larger than 1. Okay, so in the next part, I'm going to talk about the implicit bias. So actually, so in traditional machine learning, so for many models, people there's a traditional wisdom that if you train for a long time, it will tend to overfit. Therefore, early stopping, or if you add some certain regulations to constrain the capacity, is useful for generalization. But in deep learning, such trick typically is not very useful, and people asked why. And actually, so this has been studied in previous work, and then people have discovered that actually the optimization algorithms, especially the stochastic gradient descent or gradient descent algorithm, actually implicit introduce effective capacity control. In particular, there's a line of theoretical work on this. And I will only mention the most related one. For example, Sodrat and Nixon et al. They show that for linear logistic regression, and they just train this without adding explicit regularization, and they show that for linear separable data, the direction of the solution converge to the hard margin support vector machine, meaning that it implicit maximize the margin for linear logistic regression. And also they also extend this linear logistic regression to deep linear logistic regression. Deep here means that we stack a few linear layers without any nonlinear activation. And another very related work is by Gonaska et al. And they did they studied deep linear convolutional network, and they show that the result is sort of implicit bias towards the separators that in some sense sparse in frequency domain. Actually, it minimize a certain non-convex norm. And also, we et al. Show that if we add some regularization, it converge to, and we make this regularization parameter smaller and smaller, it converge to a max margin solution. But the question is whether for a general deep neural network, so we have such a max margin phenomena or implicit bias. So here in our work, we studied this so-called deep homogeneous network. So here homogeneous, K-homogeneous means that if we multiply the input by alpha, the output multiplied by a factor of alpha to the power of K. So actually this is true for Relu network if we don't have a bias term. Here, just to remind you, so for each linear layer, we usually have AX plus B, right? If there is no B, we only have AX, it's homogeneous. And actually, we did the experiment. So even if you remove the bias, so the performance of the neural network would be similar to the one with bias. So therefore, it's a fairly general class of neural network. And here we assume the training loss is just a standard classification loss, surrogate loss. So it's for example, you can use the exponential loss or logistic loss. So, and we can prove our result for more general loss with exponential tail. And both loss can be see as surrogate for 0-1 classification loss. But right now we cannot prove this for hinge loss. So in order to present our result, so we need to recall the classical support vector machine. So this is a convex optimization formulation for support vector machine, and we want to sort of minimize the norm, and subject to this margin is larger than 1. This is well known to most machine learners. And we can equivalently write that we want to maximize this as a margin, and subject to for every data point, this is a geometric margin which is larger than m/2. So these two are equivalent, and we can generalize this linear support vector machine to the deep learning case. So we can similarly define the margin to be for the data point xn and yn. The margin is yn would be +1 or -1, and this theta is phi is the output of the neural network, and we want the output of neural network has the same sign as yn. So if this is large, positively large, then we have a very good margin for this. And the margin for the instance is the minimum margin of any training data point, and we hope this margin to be as large as possible. But the thing is that because the network is homogeneous, actually we can scale the parameters and the margin will also increase. So this doesn't make much sense. So we have to consider the right notion of margin. So actually, the correct notion of margin is that we have to normalize the margin somehow. And similar to the linear case, we normalize the margin by the norm of the weight. So in the deep case, we normalize the margin by this factor. Basically it's the norm of the parameter to the power of L. So we consider this margin. So this margin must be normalized by this factor. And I'm not going to explain why. So this margin is the right notion to consider, but just believe me, this is the right notion of margin that properly generalize what's happening in the linear case. So our goal is we want to show that so as we train this neural network, so that we somehow implicitly maximize the margin, but directly analyzing the margin is even the normalized margin is very hard. So actually we consider a smoothed version of a margin here. So basically what we do is we change the max to we change the mean to soft mean. So recall that the margin is defined by the minimal of those points over those points. So we change the minimal to the soft mean. So basically it's a log sum exponential term. So actually it's easy to show that this smoothed version can be sandwiched by the actual margin up to a very small additive factor. So this factor will converge to 0 as we train the neural network. So therefore, in the later stage of the training, this is very, very small. So therefore, the smoothed normalized margin is very close to the true normalized margin. And here, let me present our main result. So for simplicity, we consider the gradient flow. So here, we just imagine that we have very small learning rate. So the trajectory would be a flow, and according to this differential equation, meaning that it goes in the negative gradient direction. And because we want to include ReLU, so but for ReLU, there are some points that are not differentiable. Therefore, we have to consider sub-differential. It's called Clark differential. It's actually a set, so therefore we use inclusion here. So our main theorem is that we can show that as after a certain point t0, meaning that in the later stage of the training, so our smoothed normalized margin keeps increase. So its derivative with respect to t is a lot greater larger than 0. And also we gave so the second point is almost the same as the first one, especially that so either we have the margin decrease or we have the fixed direction. So this is a direction of our parameters, and this is the normalized margin. Smooth normalized margin is close approach to the actual normalized margin. And then we gave also a very tight upper and lower bound for the dynamics of the loss function and the parameter. Okay, so this is a very tight characterization. So, but also holds for the late stage of the training. And our second result is that actually, so this gradient flow implicitly solve the max margin problem. So actually, we can formulate for the deep learning regime, we can formulate the max margin problem, which is very similar to the classical optimization support vector machine optimization problem. You can see it's a strict generalization, and for this max margin problem, we show that actually our gradient flow training. So the every limit point of this direction is a KKT point of this max margin problem. So the KKT point is basically the first order optimal point of this optimization problem. But without any other assumption, I mean, this is a highly non-convex problem, and it may have many local or global minimal, and so the best we can hope for is to prove that it approach to a local minimal, or here we can only prove it approach to a stationary point. And there is a independent concurrent work and prove very similar things, but they have to assume some other convergence result. And we actually use much weaker assumptions. And as a corollary of the previous result, actually we can show that in the later stage of the training is actually sort of implicitly solve the kernel supported vector machine. And this kernel is a so-called neurotangent kernel, which is a very hot topic in recent years. And this is a kernel supported vector machine. And this is the feature map of that kernel. And you can see it very similar to the SVM formulation. And now let me just, I'm not sure how much time do I have. So
you can have 7 minutes or more.
Okay, sure. Okay, let me present some experiment result. So this is so we train a standard homogeneous network, and we have also done some experiment for non-homogeneous network with bias, and we find that the performance are very similar. And so as we train more, we can easily get 100% training accuracy, meaning that we have classified those data points during the training. And also the training loss keeps decreasing. You can see this as exponentially scaled. And you can see that actually the normalized margin increase slowly as we keep on training the neural network. And actually it increased very slowly. And actually our theoretical result gives the actual rate. And actually we did some more. Actually we can sort of increase the learning rate based on the loss. If the loss is very small, we can increase the learning rate, because at the end of the training, the landscape is very flat. So we can increase the learning rate somehow because the gradient becomes somewhat small. And we can see that as we train for the 10,000 epochs, this is a training loss keeps getting smaller, and it becomes really small. And we have to even change the TensorFlow, the precision representation, and you can see the normalized margin keeps increase. Okay, and it's pretty consistent with our theory. And at last, I want to mention the sort of the connection between robustness and the margin. And I guess many people know the adversarial examples in deep learning. And so basically, it says that if we add some very small adversarial noise, then it can destroy the prediction of the deep neural network. For example, in this example, it changed the prediction of Panda from 57% confidence to Gibbon with even very high confidence. And this such adversarial example is a very hot research topic nowadays, and people want to develop robust deep learning model so that it resilient to such noise. And also, so it's easy to imagine that if you have a very big margin, that it perhaps the model is more robust. And we did some experiment on this, because we show that if we keep on training, the margin will increase, and therefore we want to see if the robustness will be improved. So here the robustness, so basically this epsilon is the robustness parameter. It means that the arrow, the size of the arrow, and we want the curve to be as high as possible. So the higher the better. And we have trained 5 different models. So for 5 different models, we have trained more and more epochs, and hopefully the margin will become larger and larger. And we hopefully the model 5 is better than model 1. And let's see this in this figure. And this is a model 1, and this is a model 5, meaning that with a certain perturbation radius, and we have a higher accuracy for model 5 than model 1. Okay, and the second figure is just this figure is just a part of this figure. So we can see that we can increase the radius, perturbation radius, from 0 to 8. But I just want to mention that our work is, we just want to see whether increased margin is useful for robustness or not. And our work is not particular focus on increasing robustness, but maybe training longer is useful, and maybe it may be combined with other robustness methods, such as, for example, data augmentation or other regularization, maybe randomized smoothing or some other tricks. Just to conclude, so we have shown some new generalization bound for stochastic Langevin dynamic, and so we connect the sum of the gradient variance over the trajectory to the generalization, and our bound is data dependent and can somehow explain the random label experiment. And we have also show the gradient descent, the implicit bias of gradient descent, and we show that it implicit maximize the normalized margin in the later stage of the training, and it's sort of the later stage is also equivalent to the kernel support vector machine, and it can potentially increase the robustness. And one of the open questions for the generalization part is that whether we can handling the discrete noise. So right now we can only handle the stochastic Langevin dynamic. We have to add some Gaussian noise, but whether we can handle discrete noise and get similar result is still an open question. And I just want to mention that the noise structure of the stochastic gradient descent is very complicated. It's a discrete noise, and in most of the cases it's yield conditioned, meaning that the condition number is very, very large, and it only is, in many cases, because the dimension is very, very high, and the noise only span a subspace in this high dimensional space. Okay, that's pretty much I want to say. So my talk is based on the last 2 papers, which was appeared in iClear this year. That's all. Thank you.
Yeah, thank you. Thank you very much. And here are some questions. The first one is it possible to reach a better generalization bound by replacing the normal noise to other noises or regularization factors?
So actually, we have some result about other noise. For example, you use Laplacian noise or some other noise. I cannot say that it will get a better generalization bound, because here we have a trade-off. So let's look at this generalization. So maybe we can do some experiment and see it's getting smaller and smaller. But here, actually, so if you add some other noise, so first of all, you have to show that, I mean, here we consider T to be the time step where we have the training must converge. So we usually consider the interesting case is where this T, we have trained this many iterations, and So if you use other noise, we have to do some experiment and see how many iterations it need to converge, for the training to converge. And so as I mentioned, if we increase the variance, and the training will become slower. So this quantity becomes smaller, but this quantity becomes larger, and it's a trade-off, and it can be only verified by actually doing the experiment, actually doing the training.
Yeah.
And then possibly there might be some other noise that you can empirically show that it has better bound.
Mm-hmm. Yeah. Another question is, does the experiment concerning margin used by SNM loss as loss function?
So that's a very good question. Actually, we have to consider this, use a different notion of the margin. Here, this normalized margin. So if you directly use the support vector machine, the margin defined in a linear case, actually it doesn't really make sense. So because actually if you keep on increasing the parameter, so the quantity will become larger and larger if you use the ordinary support vector, the ordinary margin definition for support vector machine. So you have to generalize this notion a little bit.
Okay, thank you. And one more question. Is there an example application that is a success of this method?
So which example?
Do you have one?
Success of this method. Which method? So
yeah, using your the technique you used here, I assume.
So I guess so for both work. So one is for generalization, one is for implicit bias. So our primary goal is to sort of provide a theoretical explanation to either the generalization or to the max margin phenomena. And so we are actually the algorithm that we investigate are pretty standard, just a standard stochastic stochastic gradient descent, and we use standard architectures, and so we focus more on explaining things, not developing new techniques. So
right.
We found that training longer is useful.
I assume the question might be like is in this sense that might be this would it have like shed some new insight in the way you conducting you are doing in practical situations. Yeah.
Oh yes, of course. For example, the last part, so if we can maximize the margin, we can increase the robustness, and we can increase the robustness of our model. And actually, recently, so we found that so somehow increase the margin only slightly improve the generalization. And the traditional theory tell us if you have a bigger margin, you have a better generalization. But in our experiment, it's not that case, and we are pretty surprising. And we are still trying to investigate. And the deep learning theory is very complicated, and so I guess we have some answers, but most of it we are we still need to study more and to give a more satisfying answer.
I don't have any more question from B Zan. Do we have any question from our audience in the Zoom? No? Okay. If no more question, let's thank the speaker again.